Hi everyone, I'm Monica, and in this presentation, I'm going to talk about the paradigm shift with the ultra-thin and flexible silicon chips, the future of semiconductor technology. Before I get started, let's go over the outline of this presentation. This presentation is mainly about why we need these ultra-thin flexible silicon chips to make our lives easier, how we can fabricate them through the chip fin process and wafer back thinning, and what are the various applications of these silicon chips such as wearable technology, printed electronics, and invisible electronics? Just imagine, you need to catch an early morning flight. As you painstakingly get up early, like I do, head for the shower, still groggy, a tiny flexible chip in yesterday's clothes reminds you that they need to be washed. Not just that, some appliances will be automatically switched into the standby mode when you leave the house through the sensors in the carpet and the wallpaper. When you get to the airport, your smart ticket guides you to the nearest exit and your smart passport and a retinal sensor give you immediate clearance. Wouldn't that be great? Such seamless integration of computing into everyday life isn't here yet, but it's not very far from becoming ubiquity. Radio frequency identification tags, also known as RFID tags, are used to track goods and even pets and people. Flexible sensors in bendable displays are on the way for e-readers. Animated color displays are even printed on washable materials. Nowadays, these flexible products can be mass-produced and can even be printed to create large displays. We can also print rollable keyboards and molded car antennas. Currently, silicon chips are built on wafers which are 100 micrometers thick. If we go below 50 micrometers, the chip fractures under its own weight. But below 50 micrometers, an interesting thing happens. The chips become flexible and more stable. Further reducing the thickness to about 10 micrometers makes the chips even transparent. This opens up a huge window of applications such as those involving bendable surfaces, windows, and car shields. And here's the icing on the cake. Thinness also enhances stackability, which is required for fabrication of three-dimensional integrated circuits. You must be wondering, why do we need to make the silicon chips thinner and thinner? There are various advantages for doing that. First and foremost is better packaging density. The smaller the chips, the more number of chips can be packaged onto a single circuit. Also, as we've seen earlier, thinness also makes the chips more flexible and more reliable. We can create various stacks of these chips for three-dimensional circuits. Lastly, thinner chips also provide better yields. It's a win-win scenario. The ultra-thin chips which are processed nowadays are primarily made from non-silicon organic and inorganic semiconductors, including polymers, but they don't perform as well as the conventional silicon chips. Silicon is an ideal semiconductor for such flexible chips. Its ordered structure allows for faster circuits. Now, we'll see how we can make these chips thinner. The first and straightforward way is to make a conventional silicon chip and grind away that base. This can be done after the circuits are drawn on wafers and before they are diced into chips. Another way is to build a thin film of silicon on a layer of oxide which lies on a thick silicon substrate. These are called silicon on insulated wafers. The silicon is then removed selectively and uniformly. But both these processes have their drawbacks. Grinding and dicing introduce crystalline defects and cracks at the edges of the wafer. Both approaches also need handle substrates to provide mechanical stiffness and stability. The device is bonded and then debonded to these handle substrates. And the separation of the chips from the handle substrates by wet or dry edge removal appears to be impractical because of high aspect ratio of the etching path underneath the chips. At the Institute for Microelectronics, Stuttgart, Germany, a new technology is being developed under the trade name chip film. The chip film technology features an additive approach in defining the thickness of a thin chip. It builds chips on slits and then snaps them off. Let's go through this process step by step. First, a porous layer is etched onto the top micrometer of a conventional silicon wafer. Next, below this top layer, a 200 nanometer layer is etched with coarser pores. This is followed by sintering of the wafer at high temperature, which means that the coarser pores close in into a cavity. It's kind of like a hall of pillars, with the pores being the pillars and the hall being the cavity. This produces a high-quality smooth substrate. Next, the fabricators build a thin layer of crystalline silicon on the substrate which carries the electronic devices. Almost all the electronic devices are located on this top layer, and it is this top layer which is of utmost importance to us. Integrated circuits are now constructed on the top layer of the crystalline silicon using standard lithographic methods. Dry etching is usually preferred as it induces lesser damage to the crystal compared to wet etching. The next step is to etch trenches right through to the underlying cavity, leaving only anchors at the corners or regions, which results in a structure perched on top of the pillars. This is done to keep the chips in a weak attachment to the substrate. Finally, the most important step. A pick-and-place tool grabs the chip from above, snaps it off the pillars, and removes it from the wafer, and we have to ourselves an ultra-thin flexible silicon chip. The chip film wafers are roughly 20 micrometers thick, which is sufficiently thick for leaving them unsupported, yet thin enough to be able to expose them to binding tests. In part A of this figure here, we can see the cross-sectional scanning electron microscope image of the chip film wafer after etching, sintering, and epitaxial growth. In the inset, there is the cavity left after sintering of the wafer. After the chips are trenched along the sides, only anchors are left at the corners so that they are weakly attached to the substrate. In this third part, the chip is first picked by attaching, then cracked from the wafer, and then finally placed in the required circuits. This is done with the help of an automatic pick-and-place tool. Now this is a really interesting image. It shows the wafer area from which some chips were broken off. The dark area in the middle shows where the chips were. In the insert, a conventional and a chip film die are shown in comparison, and we can clearly see that the chip film die is a lot more thinner than a conventional die. There are some specific issues in the wafer chip processing and handling. As seen below, the wafer can fracture due to its own weight, and the edges of the chip can get clipped. Apart from these, crystalline defects are also introduced in the grinding and dicing of the process. Even if we manage to get an ultra-thin wafer without any damage, there are some other problems with the ultra-thin chips as well. First and foremost is the cost factor. They cost about 10 times as much as conventional wafers and require extra substrates during handling. On top of these, the techniques waste about 99% of silicon wafer, as only the top layer is utilized for chips and the rest of the base is ground and diced away. Even though the chip film process makes chips as thin as 10 micrometers, it's not yet ready for large-scale production. After finishing, the prized flexibility of these chips make them hard to attach to a substrate. Bubbles can also form between the substrate and the chip. If pressure is then applied to the chip, these bubbles can fracture and die. Now that we've seen the why and how part, let's go to the what these chips can do part. The mechanical flexibility and reliability of these chips is exploited in the security chips in passports or bills, high voltage driver chips in flexible displays, and radio frequency identification tags. Smart cards need thin chips for form factor reasons. Also, power dissipation to the package is improved if chips are thinned down. Back-illuminated CMOS imagers are feasible only at the minimum chip thickness. These ultra-thin chips have carved a niche in the medical field as well. Miniaturized chips are used in video endoscopes and diagnostic pills. They're also used to form biomedical chips such as subretinal implants. They need to be extremely thin so that they can adapt to the shape of the retina. Their ultra-thinness also makes them extremely efficient as stacks required to form 3D integrated circuits. Perhaps the most promising field of application of these flexible chips is the wearable technology. There are mainly two types, apparel and devices. Apparel includes weavable, washable, foldable and printed transparent chips which can blend in with the clothes. The other type, the evolutionary devices, are typically mobile phone peripherals or variants with new human interfaces. Many big companies such as Intel, Google, Samsung, and some more are investing in this technology. The printed electronics use standard or in some cases slightly modified printers such as those used for inkjet printing or laser printing. It is the inks used in these printed electronics where the innovation lies. These electronically functional inks are used to print working and purposeful devices such as thin film transistors. The inks are made from semiconducting organic carbon-based materials in a solution-based format, making it possible to deposit materials onto a surface using additive or printing techniques. Currently, there are two major applications of the printed electronics, the smart window and the e-paper. The e-paper looks and feels just like a regular paper, but it does much more than that. It stores and displays information like the newspapers in Harry Potter movies with moving pictures in them. It's no longer a magic. The smart window is installed just like a regular window. It has a thin transparent film on one side which allows users to control the amount of light and heat passing through it. The best and my favorite application of these ultra-thin chips is in the invisible electronics. Nowadays, it is possible to include electronic components to almost everything with printed and transparent electronics. It can be done by simply applying a plastic film on the surface, as the see-through circuits and power supplies have already been printed onto it. Finally, the conclusion. Right now, we are at the beginning of this new world with modest initial victories such as rollable keyboards. Animated printed posters with sound interactivity and other electronic features can be seen at the Tokyo subway. They're unrolled and applied just like regular paper poster and capture the low level of lighting available using printed OPV. The latest on the market are apparel, bags and parasols that can charge our phone. It's not very far when the ultra-thin flexible chips would become an inseparable part of our lives. Here are some references that I've taken aid of for preparing this presentation. With that, I'll end this presentation. Hope you liked it. Thank you.